Hello everyone. In this video, we're going to finish up talking about linear regression, which was the subject of the last video, and then finish up the whole lesson. So I've given you a line of best fit, which I call the linear regression line, and we've talked about interpreting that line and using that line to make predictions about new values that I don't know. Okay, but what I didn't cover is how do you actually create that line? Okay, or what do I mean by line of best fit? Okay, we kind of glossed over that. This is where we'll talk about it very briefly. Okay, so what do I mean by a line of best fit? So I've got some data here, simple data. There's no units associated with it, but it looks like I have a linear relationship and I can put a line through it. The question is, which line do I put? So it turns out that there are an infinite number of lines that quote unquote go through the data. Some are good and some are not so good. So for instance, here's a picture where I have the same data set as in the last slide, but I put a bunch of different lines through it. And so you'll see some of them are good, some of them are not so good. Okay, certainly the orange line, and I'm sorry if you're colorblind and looking at this, you may not be able to tell the lines. Please let me know and I will make my graphics colorblind friendly in the future. Okay, so certainly the orange line, which is vertical right at 30, is not a great representation of this data. Okay, also the dark blue line that actually shows a downward trend, also not a great line. Okay, the green one shows no trend or no association whatsoever, probably also not great. But then I have the red and then the purple. And the question is, the red line is positive and it actually goes through a number of the points, whereas the purple line tends to fit the overall pattern, even though it doesn't actually go through any points. Okay, certainly if you looked at this, you'd probably say, yes, the purple is the best. But why is it the best? Okay, so that's what we're going to define here. So how do I choose which one is best? Well, I have to use math to get there. Okay, so I have to use mathematics to get there. And so I have to define what makes a line good and what makes a line bad. And so the thing that people settle on is what makes a line good is that there's not a lot of distance between the points and the lines when I look at all of the points together. And so we have to define a new term for looking at the vertical distance between the point and then that line, and we're going to call that a residual. Okay, the vertical distance between the actual and predicted y values for a particular x value. Okay, so I'm at the same x, and I look at where that line is for that x value and also where the point is. And so that the distance from the point to the line is called a residual. All right? And so it turns out, I won't talk through it. I usually do in other courses, but not for this one. The line, the best line, is the line that minimizes the sum of squared residuals. So if I take each of those vertical distances, I square them all, and then I sum them all together. The line that has the smallest of that number is the line that wins. Okay, so it's the line that has the smallest of this value. Again, we don't need to worry about that. There are mathematical ways to get that very easily, okay, and we're going to use software to do it. So we don't really have to worry about this. And you can actually go farther and use stuff that we already know to describe or create formulas that make the slope and the y-intercept for that line. And so the slope which is b in our original equation, is actually the correlation coefficient that we talked about before, r, times the standard deviation for the y data divided by the standard deviation for the x data. Okay, so that's the slope. The y-intercept is the mean of the y's, y bar, minus the slope times the mean of the x's, or x bar, and so that gives you the y-intercept. You again don't need to know these formulas. I'm not going to make you calculate them by hand. I just want to give them to you for completeness. And so here's the point that I've been making the whole time, is that in practice we'll always use software to find the line. Okay, so we can StatCrunch or Minitab will find the line for you. I want you to know how to interpret that line and how to predict with that line. So that's the real punchline, the real takeaway that you should take away from this lesson. Okay, so that's how to actually make the line. Then the final question that we're going to talk about in terms of linear regression is, after I've made the line, I need to look retroactively and say, did that line do any good for me? Was it worth it? Was it worth all the time and effort to make that line? Okay. And so to do that, we can actually quantify that with a single number. And that number is called r squared. Okay. So it's called r squared. We've made the line, but is it useful? And so another way to rephrase that is, did using a line to describe the relationship between x and y gain us any predictive power versus just using the mean of the y variable? Now, that's probably very confusing. But for instance, let me give you an example to try to make it easier. We'll take the car example where I have city versus highway miles per gallon. So if I bring you in a car, okay, I bring in a car, put it behind my black curtain, and then I ask you, without telling you anything about that car, predict the highway miles per gallon of this car. What would you do? Well, if you had no information about the car, but I give you some data about cars in general, and I give you their highway miles per gallon, nothing else, your best guess is probably, or once you learn a little bit more about statistics, should be the mean of the y variables. Okay, the mean is the center, and it could be, depending on the type of data, where a lot of the data lie, but not necessarily. But the mean is the best guess if there's nothing else available. So I tell you nothing about the car. I only give you some data on highway miles per gallon, and I ask you to make a guess about what the highway mile per gallon of this car is. You're going to say, well, I don't know anything about the car, so my best guess is 20 miles per gallon, which is the average for all cars. Okay? Now, what if I say that there's a relationship, or maybe there's a relationship between city and highway miles per gallon? Okay, certainly there is. If I tell you, wait, instead of having no information on this car, what if I tell you that this car has 35 city miles per gallon? Does that inform you on what the highway miles per gallon of this car could be? And you should say yes. If this car has 35 city mpg, then it's very likely that the highway mpg of the car is high. Okay, if it's getting 35 miles per gallon in the city, it's probably going to do pretty well on the highway. So, using that line, gave you a lot more predictive power than just like the baseline prediction, which would be the mean. Okay, so that's what R squared is measuring. So hopefully that made it a little clear. So the gain we measure with R squared, which is what I said before. It is literally the correlation coefficient R squared. Okay, so I take the correlation coefficient and I square it, and now that's called R squared. Another way, another term that we use for R squared is called the coefficient, or another thing that it's called is the coefficient of determination. Okay, so the coefficient of determination, or R squared, is literally R squared. So it's interpreted, one way is to interpret my in other words up above. Okay, another way to interpret R squared is the in other words up above, or it's interpreted as the percent of variation in Y that can be explained by the linear relationship between X and Y. I'm not really going to get into that interpretation now. I think the other one is much better for this course. So for example, in the city versus highway MPG example, R squared was 0.76. Okay, and that means that our predictive power was increased by 76% in using that line versus just the mean of highway MPG. Okay, so we've done pretty good there. So here's another way to do this. This actually gets to that second interpretation that we're not going to use, so I'm actually going to skip over this slide and go here. Properties of R squared. Because R could go between -1 and 1, when I square those things, R squared is between 0 and 1. Okay, 0 is when there's no association. It means that fitting a line to that data does not help you at all in making predictions. When it's 1, that means it's a perfect association, which in turn means that using that line, you can get perfect predictions of Y when you have X, okay? Because the data is literally a line, all right? And so everything's going to be perfectly on that line. So here's a reading assignment about the stuff that we've talked about in 113 through 123. We'll talk about coefficient of determination and making a linear regression line. All right. And so there's, in the last minute or so here that this video will go, I want to talk about some cautions of doing regression. And so these are things that you'll actually see in real life that people do, but are bad ideas. Excuse me. So the first is that extrapolation is dangerous and risky. So what do I mean by extrapolation? What I mean is that I use that line that I made for predictions outside of the range of data that I have. Okay, so as an example, in our cars example, city versus highway MPG, it would be meaningless and maybe dangerous for me to say, I want to find the highway MPG for a car that has 200 city MPG. Certainly there is no car that gets 200 miles per gallon in the city, okay? And so it would be meaningless for me to find the highway one. Another example is height, maybe height versus weight, okay? Certainly humans can only be so tall and so weigh so much, okay? So after I get outside of what's reasonable, then the predictions become meaningless. And so that's what I mean by extrapolation is dangerous/risky. Excuse me. The second is that outliers, which we've talked about before, can really affect the regression line. So I have a picture here. Okay, so I have some data that looks to be linear here, and then I have an outlier that's away from the general pattern of the data. Okay, it doesn't fit anything else. And so if I fit a regression line without the outlier and then one with the outlier, I see how much that this point affects it. And so if you look, the line in constant red, okay, is, or the full line in red without the outlier fits that data fairly good, okay, really well actually, okay, and sort of tells that story. But if I add in this outlier down here, it really, and so you'll see that line in as the dotted line, okay, you'll see that it really pulls down that line away from the general pattern of the otherwise non-outlier data, okay? And so these outliers can really affect your results. So if you ever find yourself doing a linear regression, fitting a line to data, you have to be cognizant of whether there are outliers or not. And what do you do if there is an outlier? Sometimes it could be due to people entering the data wrong. So maybe it's just a weird error. And if that happens, you should take it out and just forget about that point. But if it is a real point, then you've got to think about, should you be modeling this data with a line? Or is there something else happening there? So you have to think more deeply about the relationship and what's going on. All right. And then the last one is a very important point that you'll see a lot in real life. And it is the broad statement that correlation does not imply causation. Okay? And what that means in my smoking and lung cancer example that I talked about in the first videos of this lesson is that you can say, or it seems generally accurate, that there is a correlation or there's an association between smoking and lung cancer. Smokers are more likely to get lung cancer than non-smokers. But it doesn't mean that smoking causes lung cancer. Okay, that is a strong statement. There are other things that can cause lung cancer. There are people who don't smoke that can get lung cancer. There are people who smoke for their whole life and do not get lung cancer. There is a correlation, but it's not a causal relationship. A causal relationship means if this happens, then something else will happen. Okay, so you see these type of statements all the time in the news, certainly around this weird time. All kinds of statements, and you need to be cognizant of what people can and can't say because oftentimes those statements are wrong. And so I have an example here. There can be an association between two variables without one causing the other to occur. That means you can have a correlation without the causation. Causal relationships only occur when all other variables and their relationships have been accounted for. And so that means you have to take into account everything that can possibly happen. And if you can do that and still say that there's a strong, there's a really strong relationship between X and Y, and there's nothing else that could possibly account for that, then you can say it's causal. Until you do that, it's only a correlation. It's not causation. So here's an example. I have a scatter plot here of the percent for different countries the percent of their population who completed high school is on the x-axis, and then the crime rate of that country in some weird units is on the y-axis. And so if you look here, you'll see an interesting picture because it looks like there's a positive relationship between x and y. As the population becomes more educated, it seems that crime rates go up, which is not intuitive at all. But if we take into account another variable, which is how urbanized is that country, and so you'll see that it is a different picture here, but I promise that there's nothing like doctored about these. They just look weird, okay? If you enter, or you sort of cluster the, sorry, these are counties, not countries. If you cluster these counties by how urbanized they are, you'll see a different story, okay? So on the left, there's this positive relationship, okay, between education and crime rate, which is not intuitive. But if you take into account urbanization, you'll see that there is a negative relationship between education and crime rate, which is what we would see, or what we would expect, okay? So this is what is called a lurking variable. It's lurking in the background and can change how things look, okay, even though they aren't, even though you can't see them, they change what happens in the background. Okay, so that's where I will stop, and I will see you for